slope of the position time graph is velocity, and we just found it's equal to 2t. Now let's go ahead and look at that velocity time graph. So here's the velocity time graph. And so it would look something like that. And let's go ahead and find the slope of this. Now, of course, finding the slope of this is pretty easy. It's going to be delta v over delta t. And so the slope, we know, is going to be acceleration. And it's going to be the instantaneous acceleration, and in this case, delta v over delta t. Now that should be easy because we just found that the velocity as a function of time is equal to, or the instantaneous velocity, is equal to 2t. Well, that should be pretty easy to figure out the slope. In fact, we know what that is. And I'm not going to say it because I know you know what it is. I'm going to go ahead and use this same idea that we did here that was pretty complicated. And see if it works. And see if it gives us the answer that we know full well what that slope is. So in other words, we know that the slope is equal to the change in velocity over change in time. Which, let's set that equal to the limit as delta t goes to 0. So we've got this delta t here, let's take it to 0. So we're trying to find the slope of the tangent line of that, which will be the same as the slope of that, since it's linear. Okay, so for this, we would want to know what the velocity at t plus delta t is, and subtract the velocity at just t divided by delta t. Again, we have this problem of we're dividing by delta t, which is going to give us undefined when we take delta t to 0. But let's go ahead and plug in what the velocity at t plus delta t right here would be. For that, it would be equal to limit as delta t goes to 0. The velocity at that point would just be plugging t delta t into this equation here. So it's going to be 2 times the quantity t plus delta t minus the velocity at this point, and that would just simply be 2t. So I'm going to divide that by delta t. Again, I have the problem I can't divide by 0, I get undefined, but maybe by multiplying this out, it'll simplify. So limit delta t goes to 0 of 2t plus 2 delta t minus 2t over delta t. The 2t and the minus 2t cancel. The delta t cancels with the delta t. So there is no delta t to worry about going to 0. I just get this to be equal to 2. So the slope of this velocity time graph, which is the acceleration, change velocity over change of time, is equal to 2 with this long drawn out process, which we already knew the slope of this equation was 2. So it confirms to us that this long drawn out process does give us the right idea. And so this is the acceleration, instantaneous acceleration. Now, let's come back over here and let's look at what that position time graph equation was. That was equal to t squared plus c, some constant. The velocity we found was equal to 2t, and the acceleration that we found was just equal to 2. Now I don't know about you, but I don't want to have to do that limit thing ever again. That's too much work. Is there a way, though, that I could look at this equation to get this, and look at this equation to get this? Some kind of shortcut rule. Well, it's the same shortcut rule that we saw when we did the exploration with the Excel spreadsheets. And that is the following. What if you looked at the coefficient out front here, which is a 1, it's not shown, but we know that's a 1, and the exponent here, which is a 2. How can we use those two to get this new thing here? Well, the exponent here is a 1, so clearly when we go from here to here, we reduce the exponent by 1. And even though there isn't a t here, I could put a t. I could put t to the 0 power, because anything raised to the 0 is just 1, and so therefore it's the same as just that. So notice that's true. We went from the second power down to the first power to the zeroth power. So one thing that I see, a trend, is that the powers are decreasing. But what about this coefficient out front? If I took this 2 and brought this down and multiplied it by the old coefficient, I would get the new coefficient here. And if I took the exponent here and brought it down and multiplied by the old coefficient, 1 times 2, I get the new coefficient, t to the 0 power. So that's the rules. So the rules for finding slope. There's only 2 of them. The first one is multiply the old coefficient by the old exponent, and that's going to be equal to the new coefficient. Let's check that again. So I'm going to take the old coefficient, which is 1, I'm going to multiply by the old exponent, which is 2, and I'll get the new coefficient, 2. I'm going to take the old coefficient 2 and multiply it by the old exponent 1, 2 times 1, and I get the new coefficient 2. Well, that's only part of it. The other part is, the other half is, what do you do to the exponents? Well, you're decreasing those exponents by 1. T to the second power, t to the first power, t to the 0 power. So the decrease old exponent by 1, and that'll be equal to the new exponent. Those are the same rules that we saw in the spreadsheet exploration that we did. But I wanted to go through the actual calculus of it so you can see all of it. If you were in calculus, there's names for these rules. The names for this rule is the power rule. And you can kind of see why we're looking at the powers here. The second power, the first power, the 0th power. Okay, so here are the rules for finding a slope, which is important because whenever you have a position time graph, the slope of that graph is velocity. So those are the rules we're going to follow. Or if we have a velocity time graph, the slope is acceleration. So those are the rules that we're going to follow. But remember, if we have a velocity time graph, there's something else that's important about it, and that's the area. The area of this graph gives us the position. In other words, let's say that instead of starting off with this equation, let's say we had something like the following. We have velocity is equal to, let's say, 12p cubed. Is there a way I can use these rules to figure out the position time graph? Well, at first, since we're kind of new about this, we might think, well, let's see if we could practice these rules here. Well, these rules said to multiply the old coefficient, let's see, so the old coefficient 12 times the old power exponent, which is 3, and then I have to decrease the power by 1, so it's going to be 2. And so that would be 36t squared. But wait a second, these rules are rules for slope. So in other words, what I just found here was the change of velocity over change in time. Is that equal to the position? No, it's not, right? It's not. It's not equal to position. What we just found was the acceleration. That's the slope of a velocity time graph. So even though this is what we're thinking we're going to do, that's not quite right. Okay? We want to find what is the position. So we have to work in reverse to get to the position. So looking over here, I noticed that it has the power, second power, first power, 0th power. So if I want to work in reverse, it probably makes sense that the power is going to increase by 1. So I'm just kind of guessing here, I'm kind of playing around, but I'm thinking that x of t is going to be equal to, I don't know what this is yet, but I think it's going to be t to the 4th power. Now what's this coefficient out front? Well, maybe it's just simply 12 times 4. I mean, it's kind of what we did before. We multiplied the old coefficient by the exponent. So maybe it's simply 48 t to the 4th. Well, if that's true, if that's the position, we don't know at this point, we're just kind of playing. That means that I should be able to use those rules to find the velocity. In other words, I'm going to check myself. I'm going to take delta x over delta t, bring down the power. It's going to be 48 times 4 t to the 3rd. 48 times 4, that's 192 t cubed. Well, that's clearly not 12. In fact, that's 16 times bigger. So evidently, when I multiply by 4, that's not really what I wanted to do, because it ended up making it 16 times bigger, because I multiplied by 4 and multiplied by 4 again. Didn't want that. It's 16 times too big. So I'm on the right track though. I got t cubed. That's good. The problem is the coefficient's too big. So what if I back up? I'm going to keep the t to the 4th. That's good. But instead of multiplying that old coefficient by 4, what if I divided it by 4? And again, what I'm finding here is, the position. Let's see, we're just checking for right now. This would simplify to 3t to the 4th. And again, if that's right, then I should be able to apply these rules to it to find the slope of this position time graph, and I know it should be equal to this. So let's try that. Change in delta x over delta t is going to be equal to velocity. And I would take and bring the power down, 3 times 4t to the 1 less power cubed, and so this would be 12t cubed. Bingo, I've got it.